Okay. So I mentioned this during one of the problem sessions, but I want to record it because, okay, so we'll be talking about homology first, and for people that weren't there, and since we'll be using it more now, I want to talk about it a little bit. I wouldn't say more formally because it's a very informal introduction, but so remember how we had this space CK, which were CK of M, which were the set of k dimensional submanifolds of M. And so if you have like a submanifold, right, like my favorite manifold is the pair of cans, then you can apply like a boundary operator to this guy, and then you get a one-dimensional lower manifold, which is like the boundary of the thing. So HK of M, so notice that the K is lower over here, in quotes, is the kernel of the boundary operator modulo the image of the boundary operator. So this looks very similar to homology, except in this case what's happening is this differential operator goes from CK to CK minus 1, so it goes down a degree. And so geometrically what it does is, what does it mean to be in the kernel of D? It means that you don't have any boundary. So if we're looking, for example, at H1, then this guy is not valid because it has boundary points, but a circle is valid. Modulo the image of the boundary operator means that, for example, this guy is equivalent to two circles because of they're connected by some manifold. So to give some non-trivial examples of this, say that we have a surface. So what happens here is if we draw a circle over here, and this is something without boundary, but it turns out to be a non-trivial element of homology because you can, well, okay, so for example, in R3, the disk can be filled, the circle can be filled in with a disk, so it represents a zero class in homology. Over here, this circle can't be filled in by the disk, so it's something that's non-trivial. However, if you have something like a genus 2 surface, right, and you have this circle as 1, so like this circle, and then these two circles as 2, then these two are homologously equivalently because there's a pair of pans connecting them. So homology classes are similar to cohomology, in which they're like equivalence classes of things up to this sort of definition. So why is this useful? Well, Stokes' theorem tells us that if we were to take some cohomology class, so recall that a cohomology class satisfies that d omega is equal to 0. So if we were to integrate a cohomology class on, say, this circle, then this is equal to the cohomology class on the two circles on the right, because their difference is equal to the integral over the pair of pants of d omega, which is 0 because omega represents a cohomology class. So what this means is that if omega is a k-dimensional cohomology class, then one way that we consider it is a map from hk of M to R. So what this means is take some k-dimensional submanifold, integrate it along omega, and then if you have two different k-dimensional submanifolds which are equivalent, like for example this guy and these two guys, then you'll get the same integration number. So turns out this is a fine dimensional vector space. I was thinking about talking about the check-around complex, but I didn't want to. There's a really nice section in bottom 2 about it, so I recommend that you read it if you have the time. But you can show that the cohomology classes for a compact manifold are finite. And the idea is that you can break apart a manifold into a bunch of open sets that are homomorphic to Rn, right? But the issue is, so you can try, Rn has the simplest cohomology, right? It has R cohomology in 0 dimension, in 0 degree, and 0 cohomology otherwise. So if you apply Marguerite-Torres to such a cover, then you might be able to like get some finiteness condition on your manifold. But this is not enough, because if you look at the intersection of these two sets, then the intersection is like a cylinder which has non-trivial cohomology. So instead, what you want is something where like the open sets are homomorphic to Rn, but the intersections are also homomorphic to Rn. So for example, for the circle, one example of such a thing is to have 3 open sets. It's like this guy, and this guy. And so the intersections are also homomorphic to Rn. But then you might have like 3-way intersections and so on. So you want some sort of a open cover so that the sets are homomorphic to Rn, the intersections are homomorphic to Rn, and so on and so forth. And you can imagine that from Marguerite-Torres, you might piece these together. And because each thing has trivial cohomology and all the intersections have trivial cohomology, it's really more of a combinatorial problem. And that turns out to be what happens. And using this, you can show that any compact manifold, because you can cover with finitely many sets, it'll have finite dimensional cohomology. And so to give you an idea of how you can construct such a cover, what you can do is you can take like a simplicial decomposition. So for example, here's a simplicial decomposition of the sphere. And what you can do is you can take sort of open neighborhoods of each face. So open neighborhoods of the highest dimensional face will represent your faces. Open neighborhoods of one lower dimensional face will represent your intersections. And codimension 2 faces will represent double intersections and so on. And because they're all like thickenings of like simplices, you can hopefully see that all of those would be contractible and homomorphic to R. Questions about that? So I'm just saying that this is finite dimensional. Turns out this is also finite dimensional, so you can like sort of consider things this way. And you can sort of also understand pullbacks. Yeah.
Sorry, what's finite dimensional?
Because you can build like a finite open cover that satisfies this property, and then you can, I won't go through the details, you can check the check-to-ROM complex stuff in there, but if you like, basically if you like go through Marguerite-Torres, you have to do finitely many Marguerite-Torres steps to get up to here, right? And each one has like the simplest cohomology, it has 1 R and all the rest of them zeros. So you can match that after finitely many steps, like you won't get infinitely many things out of it. And you can also understand how cohomology classes pull back through this. So for example, if you have a cohomology class on the torus, which sort of measures this angular direction all around, so it'd be like this over here, and then like that, right? So imagine you have a map from a circle into here. So if this is some one form omega, then you want to understand f star omega, and let's say that this is this circle. So, or better, let's say that we have a cylinder. So we map it like that. So you can understand this by saying, okay, this is something which is a one form, so it integrates on one-dimensional homology classes. So pick some homology class over here, and the integral of this over here. We talked about this last week. Basically, the d f star equals f star d is equivalent to saying that you can either pull this back and then integrate over here, or you can push this forward and then integrate over here. And we saw a little bit in the problem sessions how you can use this to prove like non-triviality of pullbacks of homology classes. Any questions on that discussion? It's just a little sort of side remark, but we'll be using homology. Well, I guess today we'll be talking a little bit more about homology stuff and sort of how to interpret. So homology is sort of like the geometric side and sort of how to interpret this algebraically using cohomology. Any questions? Okay. In that case, so far we've seen in the first 2 lectures how to define cohomology, and now we've seen how to, last week we saw how to compute cohomology of different spaces. And so starting today, we're gonna see how you apply cohomology. And so what is cohomology useful for? So the idea is like cohomology and other things in algebraic topology, I guess, but cohomology is the simplest one, is useful to compute things which are invariant under deformations. So I'll be trying to talk about two of these today, which is going to be the degree of a map and the intersection, how to like talk about intersections on manifolds. Okay, so first, I guess, degree of a map. So what is the degree of a map? So if you have a map from two manifolds, M and N, the superscript denotes the dimension. So if you have a map between two manifolds of the same dimension, then what you do is you pick some point P in here, and then you look at F inverse of P, and the degree of F is equal to the cardinality of this set. So it's saying, look at the preimage of a point and count how many points there are in the preimage, and that's the degree of your map. So maybe if you haven't seen very many interesting maps, it would be useful to point out why this is an interesting object. So let me give you some cool maps. Let's say that you have a torus, right? So usually people call a torus a donut, right? So for the way that I genuinely explained this to someone one time was like, imagine you have a donut on like a kebab stick, and then you flip the kebab stick 180 degrees, right? And what we'll do is we'll identify 2 points on the torus before and after rotating. So what happens is you identify this point in the front with like this point in the back over there, right? So if you take the quotient of this, which is you sort of glue these together, what do you end up getting? So you can sort of say that anything in the front face gets identified with something in the back face. So you get something like a cylinder, right? Except stuff in this top circle will also identify stuff in the bottom of the circle. So you have to glue those together, right? So what happens when you glue up both of these circular ends? What do you end up getting? Yeah, a sphere. So after you identify this with this and this with this, what you end up getting is the sphere. And so you can see that the preimage of any point on the sphere, you're going to get two different preimages up here. This is an example of a degree 2 map. You can extend this example by saying like, okay, let's say that we have like a genus G surface, right? You can still do the flipping thing. The only thing that'll happen here is you get a few more circles, each of which gets identified, and you take the quotient again, and you get a sphere. And so this is again a degree 2 map from a genus G surface down to a sphere. Yeah? So that's sort of an interesting example of a map. Another cool example is, let's say you have something like a fidget spinner or something, right? And what you can do is you can rotate this by 120 degrees, as middle schools love to do, and you can quotient it out by this guy. And does anyone want to take a guess as to what you get? First off, what is the genus of the surface? 4. Okay. Does anyone want to guess what you get when you quotient by this action? Okay, close. So let's see. What do you end up getting? So you can sort of split this up and see that these bottom 2 parts split into 3 parts. Right? You can see that any of these parts will end up at the top part. So what you end up with is this sort of a guy with this circle identified with this circle. So what does that give you? genus 2 surface.
Yeah.
So, and what's the degree of this map?
3.
3. Yeah, because at any point, it's like taking a preimage of this point, and so you end up with 3 different copies. And you can like extend this sort of thing, right? You can consider like adding more handles. So you can get like a, I guess a degree G minus 1 map from a genus G surface, SG down to S2. Right? Because whenever you quotient, you essentially get one handle. And then you just glue those two sides of the handle, so you get this sort of thing. And then maybe an example of a degree 1 map. What you can do is you can take a surface like this and like have like whatever you want, right? Doesn't matter. And what you can do is you can say, okay, I'm gonna take this part and just like squish everything on the right down to this part. And so what you get is the surface and then a lot of junk over here, right? And then what you can do is you can like sort of contract this junk down, and then what you end up with is a torus. So what's the degree of this map?
The genus of the starting.
Okay, and how'd you get that? Other answers are also low.
Two is the degree, calculate the degree.
Yeah.
2 times the number of holes.
2 times the number of holes, how'd you get that?
I don't
So,
Like on either side of a hole.
okay, so you're suggesting that like you have something, so it's like if we look at the preimage of this point, for example, you have like this guy, and like this guy over here.
Oh yeah. I think it's 3.
Okay, so it seems like maybe from like that suggestion, like the degree would be 3. If you look at the preimage of maybe like this point, maybe like we project in a weird way, so then maybe like we project along this line, so we get, so now it seems like the degree is 5,
Is it just 1?
right? If we look at the preimage of this point over here though, it's just 1.
So it's just 1.
So, okay, sure, but like, does anyone have like objections to this definition now?
Like almost everywhere. Like the degree should be almost everywhere in the
Okay, so that's a guess, but over here, if you look at anything on this disk, right, you'll have like something lacking, so that's not almost everywhere. Yeah.
Wait, in that disk, aren't there infinite? Oh, never mind. But
Yeah,
aren't there
it kind of
infinite
like
light
is.
points on this line that are getting collapsed there? Isn't it pretty much infinite?
Well, it's kind of like you can just like draw horizontal lines, right? And like if you have a surface in 3-dimensional space, it'll intersect a horizontal line finitely many times.
You have a what?
If you have like a, well, I mean like, yeah, I guess like these points, yeah, like this outer ring which you're shrinking down to this boundary, those will have infinitely many preimages.
Confused why not every point has infinitely many.
Let's, if you take like a genus 2 surface and you sort of project down onto here, if you like draw horizontal lines here, this will only intersect a finite
Oh,
number of
right,
points.
yeah, sorry, yeah, I got confused. I was seeing that makes sense, sorry.
Yeah. But yeah, so from some perspectives, it seems like it intersects at many points. Other perspectives, it seems like it intersects 1 point. Other perspectives, it seems like it intersects infinitely many points. So this definition is a bit wrong. But it would be nice to understand pictures like this, right? To process cohomology. And so the point is that there's 2 things that you need to fix. One is that you need to account for quote unquote signs. And the second which is something about orientation, and the second is that points like this, where there's like infinitely many pre-images, those are bad. So you need to remove such points. And you'll see that that condition corresponds to having a zero derivative. So let me give one more example, which will be a lot more instructive as to what's to come. Let's say that we have something like this, and we project this down onto the line. What's the degree of this? One. Why?
Because almost everywhere, okay, because vaguely speaking, it feels like there's no wrapping. Or do you want a formal explanation?
I don't need a formal explanation, but like, don't use something like rapid. Just give me like where you see one in this whole picture.
On the left, on the right, and
Okay.
in the middle. Okay.
So on the left, there's one pre-image, right? On the right, there's one pre-image. So what were we gonna say about the middle?
In the middle, it's wrapping around, but the times when it's going to the right and the left cancel out.
Oh, okay. Yeah. So what I want to do is I want to imagine like sort of a. I think like in geometry, like if you look at static images, you can't get a good feel for things. You should look at images that are like sort of moving dynamically. So let's see what happens as this point moves to the right. So here you select one pre-image. Here you end up with two pre-images, but here you end up with three pre-images. And as was said, sort of what happens going from here to here is there's nothing, and then two pre-images like appear out of nowhere, right? But the thing is that if we orient this curve to go this way, and if we orient this curve to go this way, then this point is sort of going in the opposite direction as this point. So what happens, you get two points which are created, but they're moving in opposite directions. And so what we can try to do is we can try and count how many points are there, but we count it with a sign. And the sign says whether it agrees with the direction of the image or whether it disagrees with it. So this will be counted with a positive sign, this will be counted with a negative sign. So what happens as you go from here to here is like you have one point and then like 2 points emerge, but this one will have positive sign, this one will have negative sign, this one will still have positive sign. And so if you take the sum in this way, you still get a point, regardless of what you want. What happens at this point?
Which way is it going? Because it's like tangential.
Right, so it's going vertical, right?
Yeah.
So it's not going left nor right. So the issue here is that if you consider this as a map with some derivative, you can kind of see that it's going vertical, just sort of like tangent to this guy, right? So the idea is that this projection map will have derivative 0. And so I guess I'll say in a second why that is the property of the bad points. But just to give you a sense, so because of the tangency, you can see that the derivative is equal to 0, but you can't see it immediately, but it turns out the derivative of this map is equal to 0, and we should exclude those points. So we want to say at some point, such that none of the pre-images have the derivative equal to 0, let's count the pre-images with sign, right? Yeah.
And by derivative equal to 0, you mean derivative of the composing with the projection, or the map?
So the derivative of this map. Yeah, so now for example, let's say that we look at this example again of like taking a torus and projecting it down onto a sphere by sort of rotating it around this axis, right? So what happens now is, look at the pre-image at this point, you get a point up here and a point back here. So is there any point which does not have two pre-images? Yeah.
Would be on the boundary?
What do you mean by the boundary?
Like at the at the point where the line is intersecting the dome.
Yeah, so at these points, again, like you have a raw number of pre-images, and this again turns out to having some issues with the derivative. So in one dimension, the problem was that the derivative was 0, what should the problem be in higher dimensions?
The derivative is determinant.
Yeah, so the derivative has determinant equals 0, and this is determinant in the sense of the Jacobian. And yeah, so anyone have a guess as to how we should talk about, so in this case, we're not like moving in a direction, right? So how should we talk about whether or not like a point should be counted positively or negatively? Because for example, again, like if we take our picture of like a genus 2 surface and we project it down into the torus by like projecting this guy down to the disk, what happens on this line is that you have like a point over here, a point over here, and a point over here. So I claim that this one should be counted with positive orientation. I think this one should be counted, one of these should be counted with a plus and one of these should be counted with a minus. So how should we determine the plus and minus signs? Yeah.
One way you could talk about is like take a oriented basis on one of them and like push it forward and see if the orientation matches or doesn't.
Yeah, so I mentioned the first lecture that we're going to talk about orientations, that we'll get to it eventually, and this is when we're getting to it. So the idea is like in one dimension, like a direction is like a vector at every point, right? So in higher dimensions, you have this notion of orientation. And an orientation is a choice of like an ordered basis. And we talked about in the first lecture that if you have two sets of basis vectors, then you can construct like their wedge products, and you can determine whether or not they have the same orientation, depending on whether so we saw that if you have like omega and eta inside lambda and v, where v is Archimedean, then omega is equal to alpha eta for some real number. In fact, real number minus 0. Let's say this is also non-zero. And so we said that this determines like two orientations. And two things are the same orientation if alpha is positive and their opposite orientation if alpha is negative. And same orientation is equivalent to being able to rotate and getting there. Opposite orientation means you have to reflect. So here what happens is you have to reflect this guy in order to get the same orientation. Over here what happens is, if you look at the surface, you sort of take an orientation that looks like that. And if you sort of move this orientation over, so at this point, right, if we pick the same orientation as above, then if we slide this orientation over to here, what will happen is, this is what the orientation will look like, right? 1, 2, 1, 2. If we slide along this picture, again, it'll be like 1, 2. So when we project this down, this will have the same orientation. But then if we slide it across to this guy, then that'll be like 1 facing outwards and 2 facing upwards. And if we project that down, then, is that the same one? I think, yeah, so that's the opposite orientation, right? Because the 2 vector faces in the same direction, but the 1 vector faces in the opposite direction. And this point, again, you will have 1 facing into the board and 2 facing out of the board. So when you project that down, that'll also have the same direction. So what you end up with signs is plus minus plus, and if you add them up together, you get 1. Anyone have questions about that? Might have seemed a bit vague.
So we have these two in like the middle like circle. So yeah.
Mm-hmm.
How did we determine that one should be plus and one should be minus?
Yeah, so if you start with this basis, right, where I'm calling this guy 1 and this guy 2, then let's choose an orientation on this torus that agrees with that, so this one is 1, this one's 2. Then if we look at the image of this point over here, then you're gonna have 1 that points into the board and 2 that points upwards.
The image of which point?
So like the image of this projection. like this line particular,
Oh, I see.
the one that has 3 pre-images.
Yeah, yeah.
So if we slide this across, then 1 will be facing the board and 2 will be facing outwards. If we take this guy and slide this across to here, then this one will also have 1 pointing into the board and 2 pointing outwards. But then if we slide that further onto this side, then that will have 1 pointing out of the board and 2 pointing upwards. And these two can't be related by a reflection in by rotation in 2-dimensional space. So these two have the opposite orientation. So this one has to have a negative sign, this one has to have a positive sign. And if we consider like moving this line around, what will happen is like a similar picture where you have 1 positive here, 1 negative here, 1 positive here. And then as you move like down the circle, the negative and positive points will come closer and closer together until you find some point where the derivative is 0. And again, this corresponds to like this line being sort of tangent to this guy. So the orientation point's perpendicular, similar to how this guy, the orientation was perpendicular. And then once that happens, these positive and negatives sort of cancel each other out and become 0. So the idea is like if you pick a point on the base and you sort of move it around, then if you count the number of pre-images with these signs, you will get a number which is independent of the that you picked. Questions about that before I talk about the Durand cohomology way of seeing this? No? Okay. Is it okay if I erase this? So how do we see this in terms of Durand cohomology? The hint is like this guy. What we can do is, and we have this picture from a torus down to the sphere. And what we can do is we can pick some point here on the sphere, P, right? And sort of if we describe an orientation this way, then what we have to do is we have to like pick one like pair of vectors. You say this guy is like E1, E2. So you have to pick like one pair of vectors, say that this is the guy with this orientation, and this is the guy with opposite orientation or the state. So you can't say positive or negative orientation without some reference, right? But another way of describing orientation is we can look at V dual, which remember is like, we shouldn't call this omega and eta. We call this U and V. So what you can do is you can take some phi in this guy. So remember, this is something that looks like epsilon 1, epsilon n. And if you have some phi here, then you can say whether this is positive or negative with respect to phi by looking at what is phi of u. So whether this is greater than or less than 0, and what is phi of u, whether this is greater than or less than 0. So what happens then is like if you have a top dimensional k form, then you can determine whether k basis vectors have a positive or negative orientation with respect to this form. Does that make sense? So this is sort of saying like instead of having a particular choice of basis that you start with, instead you have a particular choice of form, and that form will tell you your orientation. So, yeah.
Wait, just to recall, what does calculating phi v look like?
That was a thing where you take, if you have something which looks like epsilon 1, epsilon k, u1, uk. I could write the formula, but you can figure out the formula based on like the alternating and bilinear properties. But what it amounts to is like taking this matrix epsilon 1 u1 up to epsilon k u1, epsilon 1 uk, epsilon k uk, and taking this determinant.
U is a form?
U is a vector. This is a form. These are k different vectors. So I'm saying that this guy is like some collection of vectors, E1, E2, up to En. So this is some basis.
Didn't you have this alternating and
Yeah, I mean, I talked about this guy, but then I said that it wasn't really useful. So I guess you can consider it as like, I want to say Vn, but I don't want to say Vn because Vn is like unordered sets. But it's like, this is like an ordered set of basis vectors.
I see.
So, ordered basis.
Sure.
Does that make sense?
Yeah.
So this is saying that if you have a K form, then you can evaluate on some basis. And if that number of values to be positive, then it's positive orientation, negative orientation. And if it values to 0, what does that mean?
You repeated.
Yeah, the thing you started with wasn't a
It's not a
basis, it was
basis.
degenerate.
Yeah.
Okay, so what can we do here? What we can do is we can take a little like bump function, kind of like we saw bump functions last week, right? And then gonna have a lot of bump functions today. So you can take a bump function around P, so that locally, or like a bump form, I guess, and it's gonna live inside omega n of this n-dimensional manifold. And what it'll be is in local coordinates, it'll look like some bump times dx1 dxn, where this is some x1 xn is an ordered basis at the point P. So does it make sense what I'm doing here? So essentially, this will, when you integrate with this form, it'll just pick up contributions near here. So what we can look at is we can look at f star, right? And so what happens here is basically this is applying the Jacobian map to this differential form. And so you get a bump form at every pre-image point. But if this guy, we also want the condition that the integral of phi over n is equal to 1. And really that's just saying that if you have a disk over here which contains the support, then we can reduce this integral to the disk. And so if you look at the pre-images, then you get one sort of bumpy guy for each pre-image, except it might have sign +1 or -1. So f star phi is essentially equal to phi composed with the Jacobian of f, right? So this is what's detecting like if the Jacobian is a positive sign or a negative sign. Whether this phi star f integrates to 1 or -1 on these disks. Does that make sense? So I claim here that if you were to integrate it along these two disks, d1 and d2, then the integral over d1 of f star phi is going to be equal to 1, and same for d2, so I'll just say d9. But if, for example, you were to look at this example again, then like if you order occurs like this, then this point over here would map with positive Jacobian. So if you have a little bump function over here, this will be with +1. This has a negative orientation. So if you were to integrate this bump function, this will integrate to -1, just because Jacobian is negative. And if you were to integrate the bump function over this pre-image, then again you get +1. Does that make sense? And so we can kind of see also where these degenerate points show up, because what happens at a degenerate point? At a degenerate point, the Jacobian is 0. So if you take a pre-image of, so if you take phi composed with Jacobian, you're gonna get 0, and so it doesn't count this pre-image. So that's why points with derivative 0 are problematic. So to refine this definition, I have to say for P, I forget the terminology. not a critical value, which means that any of these points have determinant non-zero.
Regular value?
Yes. Regular value. And counted with sign. Where counted with sign means orientation. Yeah.
In the example on the sphere, the torus, right? If we take a point and the preimage is these two bump functions that are positive and negative,
Yeah.
doesn't it mean the integral of the preimage of the pullback will be 0?
So no, because each one of these maps. Okay, so this drawing's kind of bad. Maybe if I replace the sphere with this guy, then maybe it's more obvious. So if you take this point P and have a bump function over here, then essentially this upper hemisphere and this lower hemisphere are both copies of the same picture. So if you take the integral over both of these parts, you get a positive one contribution. So the integral of this over the entire manifold is going to equal to 2.
But on the bottom it's 1.
Yes. Because if you so this is where you have to like actually analyze what the Jacobian is. So Jacobian is positive, then or like you either look at the Jacobian or look at like what it does to the oriented basis at that point. So if it preserves the orientation, then you get a contribution of 1. If it reverses the orientation, you get a contribution of -1. I'd say keep this example in mind.
Am I crazy for imagining that if we took the integral of a thing and took the integral of the pullback of preimage, we should get the same thing? I guess that's just not true. But
Yeah,
that
that
bothers me.
is indeed not true. So what you can say is, if you take a set and you look at the image of this set, then if the image is like if the image is homeomorphic to this guy, then that's true because
Sure.
that's like a change of coordinates formula.
Okay.
But if your image has like if your image like collapses multiple things, then you have to take into account each of those pre-images.
Right, that makes sense. I guess previously I kind of thought of it as like a change of coordinates, which would make this not make sense.
Right.
That makes
So in
sense.
this case, you get like multiple covers, and that's what makes the degree sort of an interesting thing to look
Sure,
at.
that makes
Pop quiz: if you have a map between two manifolds of the same dimension, which is not surjective, what's the degree? 0. By a very simple argument that if you take any point that's not in the image, the preimage is 0. So this is kind of interesting because like you can try and imagine like any sort of non-surjective map from the sphere to the sphere, you'll realize that it has to fold it in upon itself because the degree has to be 0, and so the positive and negative parts are going to have to cancel out. So that's a pretty interesting thing. So I guess you can like really complicate the statement and make it into like something which seems very non-obvious, which is if you have a map from a sphere to sphere, which is non-surjective, then you have 2 points which map to the same point. So that's something you can use. Another thing maybe is how do we know that such a regular value exists? That follows from something called Sart's theorem. Sart's theorem says that regular things which are not regular values are critical values. In other words, images of things with derivative 0 have measure 0 on the image set. Usually when I used to remember this, it was like something measure 0, something derivative 0. The easy example that I like to think to like remember this really easily is consider like taking a plane and mapping it to another space where you take the plane and crush it to a point. Then every point in the domain has derivative 0, but only one point in the image is the image has like the derivative 0. So the points in the image which come from points with derivative 0 has measure 0, which means it's like rare, which means like most points weren't calculated degree. So what's cool about the degree? I prepared one statement and I did not prepare the other. So let me see, I can tell you the one statement that I prepared. Now let's see if we can figure out the other one. So, one idea is this idea of homotopy, which is that you can like deform a map itself. And so imagine like we start off with this map onto the line, and what we do is we sort of like bring this part down and this part up, and so we change a map from the line to the line to go from this map to this map. So formally, the way that we define that is, so let's say the domain is again M and the image is N. So homotopy is a map from M cross 0, 1 to N. And you should sort of imagine this as like a movie where you're like moving, where the points move around on the image. So you're keeping the domain fixed, but you're sort of like moving where the points end up. So in this case, you're not actually moving the domain. What you're doing is like, this point would sort of move left, while this point would move right, and it would sort of, the image itself would sort of fold in upon itself. So we can show that if this is the case, then h of 0, which is the image of M cross 0, and h of 1 have the same degree. Anyone want to take a guess as to what the proof of this is?
This is the one with like lines.
Nope, there's a very simple, you can prove it with something with lines, but there's a very clean and almost stupid wrong cohomology way to prove this. So what you can do is you can consider like a form, like how we had earlier, located at a single point, right? And if we consider this like sort of schematic picture, where we have this map, so this is M, and this is the interval I, right? So this is 0 and 1. Then we're mapping this guy down to this manifold N. And what we want to compare is, so if we have this bump form, which we'll call omega, what we want to compare is h0 star omega, integrate that over M. So this will give you the degree of the map h0, right? And we want to show that this is equal to the integral over M of h1 star of omega.
Why is this the degree?
So the degree, as I explained, was the integral over S star of this bump form. So you're picking up one contribution for each pre-image.
Right.
So for example, this is saying that like each point here literally has one pre-image, and each point here has multiple pre-images. So you can sort of interpolate from one picture to the other picture, and I think that that doesn't change the degree at all. So does anyone see why this should be true?
The boundary of this same thing.
Right, so there's a boundary of something, right? So that seems to hinge towards something. So this guy is equal to the integral over the boundary of M cross I of, we can just say h star omega here. And we know that this is equal to the integral over M cross I of d of h star omega. And now here's where the proof gets really stupid. How do we finish the proof?
Swap the d and h star.
Yep, and what does that tell you?
0 because omega is closed.
Yeah. And why is omega closed? So omega is an n form on an n-dimensional manifold, right? There are no n plus 1 forms on an n-dimensional manifold. So by default, it's closed. So this is where the proof is really dumb. Because it seems like you cheated somehow, because this guy is closed just because like you have a top form on an n-dimensional manifold, but you're pulling that back to an n plus 1 dimensional manifold. So here it's closed for a dumb reason, but if you pull that back, that turns out to also be closed because of you can swap d and h star. And so that means that this integrates to 0, which is the difference of these two values. And so that tells you that degree does not depend on if you perturb the map. You can similarly prove that if you move, so this is one I did not prepare, that if you move the point on the base, then that would also not change what the degree is. So let me try and think if I can come up, or you can also think and tell me if you can come up with a proof of this statement.
What exactly is this thing?
So if you have this map, right, you can either consider P over here, or you can like sort of move P to this point Q. And there should be some proof involving Stokes' theorem again, where you have like the preimage of P on one side and the preimage of Q on the other side. And you show that that is,
Like, couldn't you move P to a non-regular value?
you could, but like on the non-regular value, like this thing just isn't defined. It's not like well defined there.
I see, so just nothing about
Yeah, so, but it, like if you move it through a regular value, go to another point, then it still is fine. Yeah, I can think of that off the top of my head, so maybe I'll leave that to think about, or maybe if I figure out a way next time, I can discuss it next time. Any questions on this guy? This one is, I think, pretty interesting. It says that if you like change the map itself, then that won't change the degree. Questions?
Wait, can you not use some sort of like continuity argument that something, the integral needs to vary continuously and the value is discrete?
That would probably work, yeah. You can say like if you move the point a little bit, then the integral would need to change continuously, as was said. But the value has to take values in integers because you're like counting something here. And so that should be fine, but it gets kind of hairy when you get near critical values, or like when two of these preimages come near each other, then like these integrals begin to overlap. It's not so clear that it will be an integer, but otherwise, yes. But there should be like a really clean proof similar to what was said over here. Other questions? Okay, so yeah, cohomology is useful for these sort of things where you're trying to analyze something, where you want to count something, and the count doesn't change under deformation, except for certain maybe like critical values. But in the generic case, you have something nice, and then you can hopefully use something like a differential form to be able to count something for that. Yeah.
What if your bump was really big?
Sorry, what?
What if your bump
Great question.
really big?
So, that's what will be on this week's problem set. We'll actually consider maps from a torus down to a sphere, and it turns out that okay, I realized the proof now.
You're welcome.
Okay, let's say that you have this point P, and you have like this one Q, right? So you come up with two differential forms, phi P and phi Q, right? And so you have this map from this other manifold M onto N, right? Now here's the thing, what is Hn of N? I guess we didn't include this, but what do you think it should be?
Sorry, what do we do about N?
The N is an n-dimensional manifold. So what do you think the top cohomology of this should be? R. Can you explain why?
Can I explain my question? Yes, because the manifold is orientable,
Why can't it be larger than R?
it cannot be larger than R
Intuitive, you don't have to give me a word.
if there's only one hole.
Yeah, so there's only like one hole in an n-dimensional manifold, right? You can't have like more
Otherwise, you need
holes.
to have
It's like,
branching. Like you would have to have a point where it's not locally Euclidean.
Yeah, something like that. So we'll like prove this rigorously later. Another point is orientability. So it turns out that for a Mobius strip, if you were to compute its H2, or like for RP2, this is why we looked at CP2 last week instead of RP2. It turns out that RP2 is non-orientable. So if you compute its highest dimensional cohomology, you get 0. And I'll talk about Hn of RP2. Of a closed manifold.
Oh,
Yeah.
okay.
Yeah. So yeah, that's a good point. Of a closed compact manifold. So we'll sort of discuss that a bit later. We'll come up with a proof of this when we discuss Hodge theory and such later on. But for now, if you have these two things, right? We said that these two things integrated to 1, right? So what that means is that if you take the difference, then this will be something which integrates to 0. Now, if it integrates to 0, basically like integration on your manifold is the bijection with R that we're looking for here. So if something integrates to 0 and it's closed because of the difference of two closed forms, then it has to be exact. So that means that this is equal to d omega for some n-1 form omega. So now, if you look at the preimage of P, right, then you're looking at the integral over m of f star P, and you want to claim that this is the integral over m of f star Q. So again, what you can do is you can take the difference here, but this time it's a slightly different argument. You still show that it's d of something, but it's d of something because these both integrate to 1, so their difference integrates to 0. And so what happens here is that this is the integral over m of d omega, which is equal to 0 because m is also a closed manifold. And so this point that m is a closed manifold is sort of important because imagine that like m was this interval mapping down to say a circle or something. Then what happens, like if you project it down here, these points will have preimage 1, but these points will have preimage 0. And the issue is that m has a boundary over here. So if you have a closed manifold, then this does not depend on the points that you choose. If you have an open manifold, if you have a manifold with boundary, what can happen is you can move and the points may disappear. So this is because m is closed. And if you want like another line here, you can say rho omega over the boundary of m, which is 0 because this is empty. Yeah. Any questions on that? So we've also shown that not only like is it invariant if you deform the map, it's also invariant if you move the point around. Yeah.
Why is it that if the integral was 0, then it's exact?
Because I claim this for now, we'll prove it later. Do you believe this statement?
Yes.
Okay, so the isomorphism of this with R, it ends up being omega gets sent to the integral over your manifold of omega. Right? So what that means is that if the integral over n is, or another way to say that is like, if you have something which integrates to something non-zero, right? You know that any other form must be equivalent to some multiple of that form. Just because of this fact. So if you have two eta and eta prime, then you know just from this that eta prime is equal to alpha eta plus d omega, right? Because the equivalent positives or multiples of each other. So if we integrate both sides of this, what we end up getting is like the integral of this is 0 because n is a closed manifold. And what we get is that the integral of eta prime is equal to alpha times the equal of eta. So that means is that the integral is it sort of gives us the isomorphism with R. Does that make sense? So now what we're saying is that because these two have the same integral, if we take their difference, that's something which has integral 0, which means that it represents the 0 cohomology class, which then because of the way that we constructed cohomology, allows us to actually find a primitive. So maybe one way to think about this is like, let's say you tried like integrating this bump form over the circle, right? So the opposite of the derivative is the integral. So you try integrating this over the circle, you get something 0, 0, 0, 0, and then something that's positive. But then by the time you got back to the beginning, you'll end up with something positive again. But if you had like a negative contribution to cancel that out, what happens once you get here, you'll push it back down to 0, and you have a well-defined integral. So if the integral of something over the manifold is 0, then you can integrate it once and get one lower form. That's intuitively sort of what's going on. Other questions? Okay. So that's degrees. So I'll start talking about intersections. We'll probably have to continue intersections next week, which means Hodge 3 will have to wait a little. But it'll be coming.
Wait, no. You should do Hodge.
Now Hodge 3 will wait. You're not ready for it yet. You're not ready. Okay, so let's talk about a similar application of cohomology, which is intersections. So let's say that you have these two circles in the torus. Okay, how many times do these guys intersect? Once. Cool. Let's say that you had these two circles in the torus. How many times did these two circles intersect?
3 times.
Ooh, I heard two different answers. I heard once and I heard 3 times.
Once.
Once. Cool, we got 2 votes for once. We're going with that. If you say it more confidently, it doesn't make it right. I mean, yeah, you can like, so the thing is like, I want to show you application of cohomology, so I'm gonna post-talk tell you that we want this to be something that we can use cohomology for. So we want something that doesn't change if we deform our picture a little bit. What we can do is we can deform this picture into this picture. And what ends up happening is you end up, again, you add up points, but these points get added with signs again. So if we count this as a positive sign, we'll have like this one's positive, negative, positive. And so what's happening over here is you have to, again, take into account like orientations of these guys. But now, whenever you look at some point of intersection, what you do is you say which one comes first and which one comes second. So let's say that this circle comes first and this circle comes second. Okay. So now if we look at these two vectors, let's say that the basis for the torus looks like this. It's like this is 1, this is 2. If we look at these two vectors, this one comes first and this one comes second, so it matches with that. If we go over to the next one, this one comes first, this one comes second, so you have to flip it. If you go around, then this one will be traveling this way, and this one's going up. So now, this is 1 and this is 2, so you have to flip that. If you go around this way, again, you've oriented the circle. So this one goes positive, and this one goes here. So this is 1, this is 2. So you get another positive contribution, and so that's how you get the signs. And so again, if you take the sum with signs, you'll get the same number. So what do I want to say? Yeah, basically, like now we're gonna try and let me first describe intersections, and maybe I could talk about the cohomology picture next time. So let me draw a nice little picture which shows that intersections are invariant under deformations of your picture. So if you, what you can do is you can go from this picture to this picture, again by sort of like messing around with this curve. And we consider that as like a space of, or as like some time-varying family of this image, of this total manifold of the torus, right? So let's call the torus M. So let's look at M cross I. I'll try and draw a big picture to see if I can make this nice. So this is M. Here's another copy of M. And U is I. So you start off with this circle, and you say that this circle does not change. So you have this circle like persisting throughout time until here, right? Now say you have this circle. This circle at the end becomes something like that. So what will happen is like, this point persists, this point persists, but this point, for example, follows out some path and ends up over here. This point follows out some other path and ends up over here. So what happens is, you can imagine like, as you sort of follow the picture of this circle through the space, what you end up with is some sort of a cylinder mapping into m cross I. So each thing over here maps to some one-dimensional higher thing in this full picture of m cross I. Does that make sense? So how does this picture almost immediately show us that if you deform your picture, it doesn't change the number of intersections? Well, we can trace out the paths that our intersections follow, right? So this intersection is going to persist and end up at this intersection, right? Now what happens to these two? Well, at some point in between, the picture that you will have is that you have this circle, and this one sort of goes around. It doesn't quite intersect, and then it goes like that, right? And then as this sort of deforms more and more up, you sort of get these points of intersection appearing. So what happens is that the path traced out by these 2 points of intersection is this sort of a guy. So like, there's no intersection over here, then suddenly 2 intersections appear and persist throughout. And so this is what was mentioned earlier about the point counting thing, which is that if you look at the intersections of these two guys, then that forms a one-dimensional manifold where the boundary components can only end up on either the initial boundary m cross 0 or the final boundary m cross 1. Does the picture make sense? So what happens here? Well, you can add like a plus or minus sign to every interval by choosing a starting and ending point. So let's say this is the starting point, this is the ending point. And the only condition that you have is that the starting and ending points have to have opposite signs. So what happens then is you have 3 possibilities. Maybe this guy goes around back, intersects this guy back here, and then comes back. So one possibility is that you have something that starts here and ends here. So then you can have negative sign and positive sign over here. One possibility is that you have an intersection that appears later, that doesn't come from before. So that means that both endpoints of this interval are the second guy. So you have a negative and a positive sign over here. And the other possibility is the sort of opposite, that you have intersections over here which disappear. So what happens here is that these intersections trace out some sort of a loop like that. And this part of this thing will sort of look like a surface over here, which contains that segment. Does that make sense? Okay, so what happens then is if we just point count, because there's only 3 possibilities, either it persists from beginning to end, or it has a negative sign over here and a positive sign over here, or vice versa. That'll say that these two guys have the opposite contributions of such arcs. Or both an arc starts and ends over here, which means that it has a positive and negative contribution over here, which cancels out. Or an arc starts and ends over here, which says it has a positive and negative contribution, so it cancels out. So at the end of the day, what you have is that the number of points of intersection over here is equal to the negative number of points of intersection over here, which is not exactly what we wanted to prove. Can someone try and see how we can fix the negative sign? How have we usually seen negative signs show up? Something O. Presentation. If we have like sort of a cylinder, right? The cylinder sort of has a starting point and an ending point. And so the thing is that the cylinder itself is oriented, and an orientation for the cylinder in this case means that you have three basis vectors, right? And this induces an orientation on the boundary. And how does it induce an orientation on a boundary? So let's say this is 1, 2. So the orientation on the boundary is induced so that this is a basis. If when you add the outward facing normal to the beginning, it becomes the basis of the bigger manifold. And I sort of mentioned this in the first lecture when I talked about the exterior derivative and how you get the signs for the exterior derivative. I said if you put this guy first, then you get the plus or minus signs to fix that. And that's the same thing that's happening over here. If you put the outward facing normal first, then the orientation is determined on the boundary by saying that the outward normal plus these guys would form the basis for this. So what happens here is that this is the outward facing normal for this, but this one's the outward facing normal for the other side. And on manifold with boundary, sort of the only canonical choice you have is outside versus inside, because you know what that means. And if you do that, then in this case, this will be the basis, because if you put this up front, then it becomes 1, 2, 3. But in this case, you have to swap the order, because the normal vector points in the other direction. So this becomes 1 and then 2. And so these two guys have opposite orientations, and that's what accounts for this negative sign, because remember we compared these orientations with the orientation of the manifold itself. And so these two manifolds have opposite orientations, but then the sign counts are also opposite, which means that if you take the sum of everything together, you're gonna get the same number. Yeah, so I have 5 minutes remaining, so let me just sketch out what I'm going to talk about next time. What we're gonna do is we're gonna take some manifold over here, and okay, last week when we talked about the co-boundary operator, and today when we talked about like taking a point on the image manifold, what sort of a differential form did I use? Yeah, it was closed, yeah. But like in the first week, remember how in the first conversation we saw differential forms were like sort of non-zero everywhere, right? Last week when we looked at the Marguerite-Torres thing, we saw that we could take the product with something which was what? What was the picture sort of like?
For what?
For the co-boundary operator?
The intermediate stuff?
Yeah, so what did it look like in the intermediate?
We multiply by these partitions B.
And then,
Took the exterior derivative.
and which was, what did it look like?
Bumpy.
Yeah, it was like a bumpy thing, right? And then we saw like, if you take a point, then like we have a bumpy thing. So I think like the first problem set that we had saw like these uniform like spread out differential forms. And now the more geometric differential forms are sort of these bumpy differential forms. And we'll see on this week's problem set that if you relate these two things together, like a bumpy differential form and a sort of spread out differential form, you get some interesting consequences. And this is what really like shows the power of a differential form being like an equivalence. And we'll see that more when we start talking about Hodge theorem. So again, we're going to talk about bumpy differential forms here. So in this case, what we're going to do is we're going to take a manifold, and we're going to take a bumpy differential form, which sort of integrates in the directions perpendicular to the manifold. So why do we want to do this? Well, let's say that we take the circle that intersects this guy, right? So if we call this manifold phi, let's call this S sub 1. If we call this phi S sub 1 and we call this S sub 2, then the integral of phi S sub 1 over S sub 2 is going to be equal to 1. Right? Do you agree with this?
You're saying S sub 1 is perpendicular to
Yeah.
S1, so it lines up with S2.
Yeah, so phi S1 is perpendicular to S1, or sort of measures the direction perpendicular to S1.
Sure.
So it lines up with S2, and
Sure.
or like negative sign if you have the opposite orientation, but like
Yeah.
assuming you have the right orientation, this is the thing. So if we modify S2 to have sort of this sort of picture, what happens? Now if you integrate it over this guy, again, you get a positive contribution when you're going this way, you go the other way, you get negative contribution, and you come back this way, you get a positive contribution, and you still get 1. So again, this is sort of like the same thing with the degree, where you have some sort of differential form which you're integrating, and that integration gives you some sort of number. And you can anticipate that, similar to what we did in the previous problem, using something with Stokes' theorem or something with exactness, you can show that these things are invariant under deformations. Okay, so what is most interesting about this is we chose a form which is like perpendicular to our submanifold, right? And to name drop a little bit, this is called the Tom class of our manifold. So we have two manifolds over here, right? We have S1 and we have S2. So what we can do is we can take our manifold S1 and we can consider this bumpy form phi of S1. And then we consider our other manifold S2. We consider our thing which is perpendicular in this direction, which is phi of S2. And one way to evaluate the intersection number is to integrate over S1 phi of S2, and sort of by a geometric argument, this should be the same as the integral over S2 of phi of S1. But there's a third thing that we can do, and that is we can take the product of these two things. So remember, on like the infinitesimal level, on sort of wedge forms, if we have something which looks like epsilon1 wedge epsilon2, and we have something which is like epsilon3 plus epsilon4, then we can take the wedge product of these two guys. It just means like take the wedge product of each individual thing and distribute by product rule. But what this is doing is this is taking the area in a plane, and this is taking the areas in two lines. And so the product of these two guys is going to be taking the areas of volumes, right? The volume of E1, E2, E3 direction, and the volume of the E1, E2, E4 direction. So what we can do here is we can extend this operation to differential forms, and we get a wedge product, which goes from omega k cross omega L to omega k plus L. So if we apply this here, and we take phi of S1 wedge phi of S2, what is this going to look like?
It's gonna be super bumpy.
Where? So what you're doing is you're essentially multiplying all the coefficients together at every point. And you're also multiplying like the differential form part of it. Okay? So over here, the coefficient of phi S2 is going in this direction. But what's the coefficient of phi S1 over here? 0, because the bump function like concentrated over here, right?
Yeah.
Similarly over here, phi S1 is 0. Sorry, phi S1 is non-zero, but phi S2 is 0. So if you take the product of these two guys, it's 0 everywhere except for which points? Their intersections, which is the only points which have something in common between them. And then what you get is something that's perpendicular to the first one times something that's perpendicular to the second one. And so you'll end up with something like a bump function times dx1 dx2. And so a third way that we can evaluate this intersection number is the integral over our entire manifold of phi S1 wedge phi S2. Now I have a question. Is this equal to phi S2 wedge phi S1?
Is what to that?
It's a good question. Is this equal to this?
No.
Why?
I feel like there should be a negative there.
It should be. So yeah, so like if you swap the two things, then on the infinitesimal level, on the epsilons, you get a negative sign. And so if you operate in different forms, you also get a negative sign. And the general rule is that if omega has degree k, and eta has degree L, then this is -1 to the power of KL of eta wedge omega. And so I always hated this because I could never figure out a good explanation for this. So let me try and give you a good explanation. So if you have like epsilon1 up to epsilon k, and then wedge E1 up to UL, what you need to do is you need to move all the epsilons past all the k's, right? So the first thing that you can do is you can move the epsilon k to the end. So I'll pick up L -1 because you're moving past L things. You can move epsilon k -1 to the end, and so that'll pick up again L -1s, and so you do that k times and you end up with k L's. And then that has all the epsilons to the right of all the mu's, and it preserves this order and preserves this order. This is called the Kozel sign rule, and there's a similar formula with the exterior derivative, which I maybe won't mention now, maybe next time. But this is kind of cool because we'll sort of, again, see this idea more. Differential forms are really nice because this over here is like an infinitesimal computation, right? But then this over here has like large scale consequences because it says that if you change the order of which manifold you consider first or second, it'll change the intersection numbers of those two guys by a possible negative sign. Yeah. Any questions on any of this? We'll talk more about this